This presentation is designed to follow the previous one on MetaNumber, the standardization of numerical information. This is an example of a network. Networks can capture information about the connections among things, a kind of information technology. It's easy to look at this and see the incredible complexity behind this network. We're going to discuss MetaNumber as a standard for numerical information. It was presented as a basis for how we can develop a new type of network. The previous presentation was to describe this standard for MetaNumber for all of numerical data. Numerical data was converted to this standard through standardized tables for future use in archiving. And that standard allowed the units, the uncertainty, and the meaning to be attached to the value. We're going to perform a network cluster analysis of MetaNumber tables as an example of how artificial intelligence can be used with MetaNumber information when it's been standardized. Networks capture information in really powerful ways. Let me give you some examples. There's the internet, that's a type of network. Electrical networks, utility networks, social, neural, transportation, and financial networks. A network should be defined. It's expressed as a matrix called the connection matrix or adjacency matrix of links between nodes I and J, telling us exactly how tightly I and J are connected with one another. The diagonal of this matrix is not defined, because there is no meaning to the link of a thing to itself. All other values are positive or zero, because nodes cannot have less than a zero connection to another node. And networks capture very unique information structures. It's one of the most powerful mathematical concepts and also one of the most difficult to analyze. Well, this is going to be one way that we're going to show how MetaNumber can support a new type of artificial intelligence. Here we discuss how we can support these standardized tables and look at the resulting standardized tables, which we call entities or rows, versus the properties or columns that will be shown here to define those networks, which will be analyzed for nodal clustering. So think of this as rows are entities and the columns are properties of those entities. Now, these clusters that we're going to find can reveal information that's hidden and not easily obtained in other ways. The resulting clusters can then be linked into what we call a supernet, or a network that spans all of this information, numerical information, and that supernet can then be subjected to still further analytics. This whole process can be fully automated, allowing a computer to constantly uncover hidden information. In a certain sense, the computer can sit and read MetaNumber tables as they're formed, and then perform this analysis and uncover this information, much like the human mind does, as we will show. I want you to consider the table of the chemical elements as an example. And think of the entities as the elements, or the rows, and the columns naming the properties of those rows or the elements. Likewise, we could imagine food names in the rows with their contents in the columns, and we're speaking here of numerical contents, the vitamins and minerals and the actual measurement of those. Or we could look at medical records and take medical records of hundreds and thousands and even millions of patients and think of each patient as an entity, even with multiple visits, and look at their properties, which are physical parameters, blood analysis, and urine analysis. And when we worked with these tables, it suggested something. I want you to think generally of a MetaNumber table as entities versus the properties of the entities. Some of those entities are more like others, like, for example, gold is more like lead, and gold is like hydrogen. So we began to ask if we can form a distance function, Cij, that reflects the distance between a pair of these elements. Then the C would define the network, and we could use our previous network research to study that network and its clusters. But we need a few preliminaries first. How do we prepare this network matrix, Cij? Well, we begin with a table S, which is a MetaNumber table. Now, as each column has the same units when evaluated with the MetaNumber engine, then we can compute for that column its mean and standard deviation. Then we make a new matrix, T, where each value in any given column is replaced by the number of standard deviations from the mean in that column. Well, these values are now normalized to have no units, as they are ratios. In other words, how many standard deviations is this number away from the mean in that column? And that becomes kind of normalized for the whole table. Then we define C as shown in this equation, defining the diagonal also as the negative of the sum of the terms in that column. Now, if the set of properties in two rows are identical, we can see that C is going to be equal to 1. And if they're vastly different, C will be equal to 0. This is really an optimal metric for a network connection matrix. Now, exactly what does that mean? Well, we've taken, in this equation, we've taken two rows, Tik and Tjk. It doesn't look like that, but it is. And we've summed that over k. So we're looking at the difference for each column between the ith row and the jth row. And we sum that over the square of that over all of the different columns, take its negative and exponentiate it. And that tells us all of the elements off the diagonal. But then on the diagonal, we take each of those columns and sum it. So you can hear I'm summing over a column for each row. I'm sorry, that should be an I right there. So I'm summing over all the rows, sum over I of Cij, and we're going to set that equal to the diagonal in that column. Next, we're going to form a new matrix, M, which is the exponentiation of a parameter times that matrix. And we can prove that this is a Markov matrix. The Markov matrix is very special. And one computes the eigenvalues and eigenvectors of this Markov matrix to identify the clusters for a given value of t. The expansion can include however many terms we want to, and it's still a Markov matrix. So we could do that exponential expansion with 3, 4, 5 terms. Now, how do we understand the clusters? Well, the Markov matrix is a transformation that represents a set of conserved flows of an imaginary substance. It could be like money, or it could be something else. It's imaginary. And that's because it leaves the sum of the components of any vectoric axon constant. The rotation, you'll recall, leaves the sum of the squares of the elements constant. The Markov matrix leaves the sum constant. Now, the eigenvectors represent combinations of nodes or clusters that approach equilibrium at a constant exponential rate given by the eigenvalue. Now, that kind of makes sense. That's kind of like normal modes of oscillation for a set of coupled harmonic oscillators. Thus, the degree of clustering can be ordered by sorting the clusters, or eigenvectors, by their associated eigenvalues. The eigenvector can also be characterized by the indices, row and column names, for the dominant components. That's because this eigenvector is going to be made up, like with the elements, it might be made of tin and copper and lead for one of the eigenvectors, and those names would be prominent in the most important part of that linear combination. In our current work, we are automatically scanning websites for numerical tables and normalizing them as MetaNumber standardized tables. And we're going to input those non-standard tables and process those into the Markov matrices as we just described. Then we execute the table normalization with means and standard deviation. Then we perform the eigenvector-eigenvalue analysis to identify the clusters. We have built automated algorithms for this processing but we really still need to build better user tools for a user to submit tables that are normalized MetaNumber tables to find these clusters. We then intend to archive the resulting analysis along with each table as it's processed and build a dashboard to watch this. What this is going to be like is as we create these tables that are normalized MetaNumber tables, they will automatically go into this standardization process with automated cluster analysis being performed, and then the computer will connect those clusters in each table to perform what we call a supernet that uses the entities and property names to link one cluster to others that have the same name. So if lead is in one cluster in one table, then lead will be in another cluster in another table. Those two will be linked. We're going to use our MetaNumber with standard tables for these calculations, and we can also do data exchange, and that's already available and useful to exchange data automatically as the computers can read MetaNumber tables with our software. We can link the user's software to MetaNumber with APIs for automated computing. That's so you can take your own software and put an application interface in that will link to the MetaNumber and automatically do the calculation. We're working to create an algorithm that will take these well-formed tables automatically into MetaNumber tables, execute the cluster analysis, and study the emerging supernet. Well, the columns or rows of a Markov matrix are non-negative and sum to unity. Therefore, those columns can be considered just like a probability distribution because they're all positive and they add up to 1. Therefore, we can do something even different here. We can study what are called the Rainey entrophies. The Rainey entrophies, like Shannon entrophies, can be computed on each Markov matrix column. With a sufficient number of those, the network and thus the table information can be expressed in a new analytical form. This is very much like a Fourier expansion in acoustic waves, and in fact this Rainey expansion gives decreasingly less important information with the higher order terms and thus extracts primary information in the first few terms. So this is a way to actually expand the topology as an infinite series or a very large series where the dominant terms really contain the main aspects of the topology. And our software performs this expansion, providing another analytic for the network and also the table data. That will be discussed more extensively in the mathematical section that follows this presentation. We take each cluster, which has a few dominant names, row or column indices, with a metric of contribution from that cluster. So we know, for example, if lead is in this cluster, we know how much it contributes because that's the eigenvalue component of the lead. Then what we do is we can attach that lead, or say here iron, to another cluster where iron has another representation as the eigenvalue as part of that cluster, and connect everywhere iron is connected in one cluster to iron in another cluster and connect them with the strengths that they are present in that cluster. And this lets us link all the clusters together with index names to such names in other clusters with a connection weight equal to the product of the values. So when zinc is in one cluster, it's connected with zinc in every other cluster with the products of those weights. As clusters are joined, this creates a single network of all numerical data. And this super network can then be studied for relationships and providing innovative analytics. It's a network that joins the hidden data or cluster information in each table. The fact that the computer will read the new tables, convert them to the MetaNumber format, and then convert them into networks and find the clusters is a powerful form of analytics. In a certain sense, what we can do is we can say the computer can sit there and just read the information as it comes in and extract that. And in a certain sense, that is very much like a human thinks, because a human thinks by clustering their information, looking for patterns, and that's exactly what this procedure will do. Well, to date, we have just begun this study, and we have studied chemical elements. We've studied financial income and expenditure tables from the Bureau of Economic Analysis, international profile data on all countries from the World Bank. We have a nutrition table that we are especially interested in that has 8,500 foods, and another one that has 16,000 foods with about 56 of their numerical properties of what that food contains. And another set of tables we've made on pollution data. And in the current work we're doing, we're finding all of these different clusters and studying how to put the software together in the best way for users to utilize. Now, the next presentation is going to be a technical presentation, and this presentation will show the background of the Lie algebras and Lie groups and Markov processes and so forth that led to these ideas. Thank you very much.